So we made it. We're actually going to do arithmetic now with all the integers, positive and negative. And actually, most of this is already done because it's all modular arithmetic. But let's go through it. So first question is, how do we even represent negative numbers? So the first approach is to use a signed bit, and it's kind of the most natural. Let's say that I have 4 bits, okay? So this here is a signed bit. And if I have the number 0, 1, 1, that's just 3, right? I put a 0 here, then it's positive, so we'll make this be 3. But if I have a 1 there, then we're going to make it negative. So 1, 0, 1, 1, that's minus 3, okay? So that's the signed bit approach, and it's pretty reasonable, right? And we could say that 0 is positive, 1 is negative, 0 is negative, 1 is positive. It doesn't matter, right? We just pick. And then we can, you know, write circuits that do that, right? So what we can do is just check, right? Compare, right? So for example, if we do addition, if it's actually a 0 and a 1, so I'm going to have to subtract. We could write the circuits to do all that. It's but it's not easy, right? So a common solution. This was kind of brilliant. Some guy figured this out. Is to use modular arithmetic, okay? And this is how this works. So I'm going to start by just making a really kind of simple assumption, and that is that I know what word size we're using in the computer. So if we're talking computer arithmetic, right? So it could be 32-bit numbers, it could be 16-bit numbers, okay? 64-bit numbers. For the examples, we're going to use 4-bit numbers, okay? Just because, you know, 4 bits is enough to actually get all the ideas across, and the numbers are manageable. So for example, the number 12 is 8 plus 4, so that's 1, 1, 0, 0. 3 is 2 plus 1, 0, 0, 1, 1. 6 is 4 plus 2, so it's 0, 1, 1, 0. 5 is 4 plus 1, so it's 0, 1, 0, 1. And those are the numbers that we'll be working with. Okay, so here's the connection. When we restrict ourselves to just 4-bit numbers, we're actually implicitly doing arithmetic modulo 16, which happens to be 2 to the 4, okay? If you're doing n-bit numbers, then it's modulo 2 to the n, okay? Now, why is that? Well, let's look at this. We have 1, 1, 0, 0, and let's say that we add 0, 1, 1, 0, right? So we go through our algorithm. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, carry 1, 1 plus 1 is 0, carry 1, okay? But we're only going to look at 4 bits, right? So here they are. Those are the 4 bits. This one actually is not part of the solution, right? It's not part of the answer. Right here is the answer, okay? And what's happened is we've dropped off that leading 1, okay? And that's the same as doing modulo 16, okay? Because this is well, it's kind of like doing arithmetic modulo 100, okay? You just have to look at the last 2 digits in base 10, okay? So yeah, that's what we have, okay? Taking modulo 16 in binary is really easy, right? Taking modulo 10,000 in decimal is very easy, and it's for the exact same reason, right? And that is that since you have a 1 followed by a bunch of zeros, then when you divide by that, really all you're doing is shifting everything over by that many zeros, right? That's the quotient, and then the remainder is just whatever was there in the first place, okay? So great, okay? That's the, we're really doing modular arithmetic if we just say we're going to use n-bit words, you know, 4-bit words, 16-bit words, whatever it is. Okay, so I want you to really truly believe that that's what's happening. So I wrote these little programs, okay? To MSB, MSB is the most significant bit. So what I do is I pass the number n, and I'm working with small numbers, 4 bits. I have to shift them over so that those 4 bits are actually the most significant bits. So I have to shift them right by 28, right? Because I have a 32-bit computer. And from most significant bits, we'll take a number, 32 bits, and then shift it to the left so that the significant bits are in the last byte. So it's just the last 4. So let's see what happens. I have 16 and 2, and I add those, right? I get 18, right? But because of this, carry effect, right? the answer that I get is actually 2, right? 2, not 18, and that's because it's modulo 16, right? Just 4 bits, right? So in computers, this is actually true, right? And this is the language C, right? And in C, yeah, absolutely, we're doing modular arithmetic, and things are, we have overflow is what we normally call it, okay? Again, let's try Java, exact same system. Java doesn't have a kind of inline function, so I have to explicitly shift and then shift back. But you notice that I get the same answer. I also get 2. So in Java, as in C, right, I'm working with 32-bit numbers. I'm doing modular arithmetic. It's modulo 2 to the 32. And so, yeah, 12 plus 6 is actually 2, when I scale it down to 4 bits. Okay, how about Python, right? And I do the same thing with Python. I shift by 28, and then I shift back. And what I get is 18. Okay, so fine. So I thought the integers in Python were 32 bits. Obviously, they're not. They must be 64 bits. So let's shift over by 60 instead of 28, okay? And what we get is 18. So Python is using more than 64 bits. Well, that's a surprise, okay? I don't know how many it has, but let's try something, okay? So we tried 100 bits, okay? And I still get 18. So at this point, I know that something is amok, right? Python, well, actually, it's not using the hardware arithmetic. It must be doing its own thing, right? It must be doing its own computations, so it's working. In this case, it works better, but I can bet you that it works slower than something written in C or Java, right? Them's the trade-offs. Okay, so let's go back to this representation problem. How do I represent -1 in binary, okay? So I have n bits, okay? And what that means is that -1, what I really want is -1 mod n, okay? Because I'm doing modular arithmetic, mod 2 to the n, okay? And -1 is actually 2 to the n minus 1 mod n, okay? There's a real simple reason for that. 2 to the n, this is mod 2 to the n, okay? 2 to the n is the same as 0, modulo 2 to the n, so -1 plus 0 plus 2 to the n should actually be the same thing, okay? So -1 and 2 to the n minus 1 are exactly the same when I treat them as n-bit words, okay? So if I have 4-bit words, -1 is actually 16 minus 1, 15, which is 1, 1, 1, 1, okay? How about -5? That's 16 minus 5, which should be 11. That's 1, 0, 1, 1, okay? Now, I want to make a quick comment here. You'll notice that all of these numbers have a leading 1, okay? And the reason they have a leading 1 is that I'm taking 2 to the n, and then I'm subtracting 1 or 2 or 3, a small number, okay? So actually, they're in the upper half of the range between 0 and 2 to the n, right? And so you might be tempted to say, this is a signed bit, okay? But it's not, okay? And the reason that it's not is, look at this number. This is equal to -1. It is not equal to -7, right? If it was a signed bit, then that would be -7 because it's minus and then 1, 1, 1, right? So I just want that to be clear, okay? Because it's really easy to fall into that trap. I know, even I'll say, oh, the signed bit is 1, so the number is negative. And that's not what I mean, right? What I mean is, oh, this is a very large number between 0 and 2 to the n, so it actually must represent a negative number, or we think about it as a negative number. All right. So if I have n bits, I have 2 to the n possible words, and what do they look like? They look like 0, 1, 2, up to 2 to the n minus 1. But notice that I am treating it as equivalence classes, okay? These are equivalence classes, okay? And the reason for that is that when I see, for example, 0, okay? When I see 0, well, that's binary 0, 0, 0, 0. And I'm actually, as a signed number, right? Meaning I'm just going to do the obvious and look at 0, 0, 0 and translate that to decimal, then that would be the number 0, okay? But I have this column that talks about unsigned, okay? I'm sorry, as an unsigned number, then that's what I have. But I have the signed columns, right? And that is, how do I want to interpret those as a negative number, okay? So for the numbers in the range 0 to 7, which are right here, right, then that just translates to 0 through 7, right? This is a convention, right? Because notice that 7 equivalence class is the same as the equivalence class of 7, and we just say, well, that's the number we meant, okay? But over here, okay, we have negative numbers by convention. Okay, so what I have are the numbers 8 to 15, right? Unsigned, but I'm actually going to interpret those as the numbers -8 to -1. Okay, so that's the important part, right? And it's a convention as opposed to any actual fact, because let's face it, when I see 1100, if I think in modulo 16, then that's 12. Okay, that is just 12. But in a computer hardware setting, I'm going to interpret that as -4. And keep in mind that -4 is equal to 12 modulo 16. Okay, so from the modular arithmetic perspective, I'm just doing 0 through 15, right? Those are the numbers that I'm using. But when I print the number, if I see that it has a leading bit of 1, then I say, oh, then I want to think of that as a negative number, right? So instead of printing 12, I'll say the equivalent negative number that's equal to 12 modulo 16, and that's -4. Okay, so that's how we do negative numbers. Okay, we simply work in modular arithmetic, and then we make a convention, right? If you're talking about 1 in the upper register of the range, then we'll think of it as negative. If we're talking about 1 in the lower register of the range, you know, the range being 0 to 2 to the n minus 1, then I'll think of it as positive. Okay. So let's finish the mystery. How do I actually do subtraction? How do I find a minus b if I have two n-bit integers? And the answer is, it's not really hard. It's just a plus minus b, right? And I know how to represent minus b. We just went through this, right? The way that I represent minus b is by thinking of it as modular arithmetic. So I just find the equivalence class for a, the equivalence class for minus b, and then I add them. So for example, let's say that I want to do 7 minus 3. Okay, well, that's just 7 plus minus 3. And now I say, what is the equivalent class of minus 3 mod 16, or 2 to the 4? And that's 13. Okay, so I really want to do 7 plus 13. And I can just do that in hardware, right? Because I have 7, 0, 1, 1, 1, 13, 1, 1, 0, 1. I add those, and I get 1, 0, 1, 0, 0. Okay, but then I remember that I am in 4 bits, so I'm going to get rid of that, and I have just 0, 1, 0, 0, right? And that's actually 4 modulo 16. 7 minus 3 is 4. Oh, thank God, right? I mean, that actually computes the right answer. Okay, but let's try 3 minus 7. Okay, so 3 minus 7 is 3 plus minus 7, right? Which is 3 plus 9, because minus 7 is the same as 9 modulo 16. That's 12. 0, 0, 1, 1, right? I'm sorry, that's what am I saying? That's 0, 0, 1, 1. That's 3 plus 1, 0, 0, 1. Okay, and yeah, that's eventually equal to 12 because it's 8, 4, 0, 0. Okay, but now there's a problem, because remember our convention? Our convention is that since this is a leading 1, okay, must be a negative number, and that's why it's so natural to call it a sign bit, right? But yeah, this must be a natural negative number, so I will actually interpret that as -4. And now I'm saying 3 minus 7 is -4. Okay? All right. So that worked perfectly nicely. Okay? How about this case? -3 minus 7. Okay. So -3 minus 7, that's -3 plus -7. No problems, right? That's 13 plus 9, because -7 is equal to 9 modulo 16. 13 plus 9, 1101 plus 1001. That should be 22, right? Which is right here. And so we have a 1 bit, which is 16, and then 4 and 2, that's 6, right? So we get rid of the 1 bit because we have 4-bit numbers, and what I have is 6. Okay. Now, it is a fact that 6 is actually equal to -10 modulo 16, right? Okay. This is a true fact. Right? But if I look at the number 0, 1, 0, 0, then by convention, this is a positive number. Right? Why? Because the leading digit is 0. Okay? So I'm actually going to say 6. not minus 10. You know, if you think of the print statement, right? So minus 3 minus 7 is equal to 6. And if you run that in C, you know, shifting 24 bits and then shifting 24 bits back, you'll actually get that as opposed to minus 10. So that's an error case, right? We call that overflow. Okay, and here's another case of overflow. Let's do 3 plus 10. 0, 0, 1, 1 plus, I'm sorry, plus 7 plus 0, 1, 1, 1. Well, that's just 1, 0, 1, 0, which is 10, okay? But again, the problem is this, is 1, 0, 1, 0, but the leading bit is 1, so we're talking about a negative number, okay? So we treat that as minus 6. Now, 10 is equal to minus 6. Modular arithmetic works, but when I print it, I get the wrong result because 3 plus 7 should actually be a positive number, right? It should be 10. But because of our convention that if a number starts with a 1, then we're going to interpret that as a negative number for printing purposes, right? Then we got the wrong answer.